Hi, in this video I will be discussing rotation and specifically looking at rotational kinematics, moment of inertia, and angular momentum. So starting off with rotational kinematics, angular velocity given by the symbol W describes the velocity of a rotational particle and can be given by the formula derivative of position. Angular acceleration, on the other hand, describes the acceleration of a rotational object and can be given or particle by the following formula: the derivative of the angular velocity. So now I'm going to go ahead and talk about moment of inertia, also known as rotational inertia. So this can be denoted by the following symbol, just like an I. And essentially the moment of inertia describes an object's resistance to a rotational acceleration. One commonly used formula to describe inertia is the sum mr squared, which is also the the integral r squared dm. And next I'm going to go ahead and talk about angular momentum. So angular momentum is a vector that describes how difficult it is to stop a rotating object. It is denoted by the following symbol. And a common formula for it is the cross product between r, the radius, and p, the momentum. Furthermore, one common formula for angular momentum is also that this is equal to the inertia times the angular velocity. So this times that. So now that we've got this basis down, I'm going to go ahead and apply this to a problem. First I'm going to read the problem and then we're going to solve it together. I do want to note though that this statement applies to 3 problems, number 17, 18, and 19, so I strongly recommend that you go watch the following 2 videos after this one. So, a solid disk of mass m and radius r is freely rotating horizontally in a counterclockwise direction with angular speed w about a vertical axis through its center with negligible friction. The rotational inertia of the disk is mr squared divided by 2. A second identical disk is at rest and suspended above the first disk with the centers of the 2 disks aligned, as shown in the figure above. There is no contact between the disks. The second disk is dropped onto the first disk, and after a short time they rotate counterclockwise with the same angular speed. So, I'm going to go ahead and make some space to draw this diagram. We've got our axes and disk number 1 and disk number 2. And then we've got our angular speed moving like that. Or I'm just going to put... Okay, and we're given that the rotational inertia of the disk is mr squared divided by 2. So question number 17 asks, which of the following properties of the 2-disk system must be conserved between the time the second disk is dropped on the first disk and the time that the 2 disks begin rotating with the same speed? So we know that the final moment of inertia final, will be equal to the moment of inertia of both disks. So inertia disk 1 plus inertia of disk 2. So we know that the inertia final can also be written as 2 times mr squared divided by 2, since we know that one disk is that, which simplifies to mr squared. We also know that the angular momentum that the we know that the angular velocity will be conserved for both. So W initial basically is going to be equal to W final. So given these two properties and the formula for angular momentum, which is, we can conclude that I inertia final times angular velocity final is equal to inertia initial times angular velocity initial, which basically says that angular momentum is conserved. And we check which option this is, and it is option B. Thank you.